This episode is brought to you by Brilliant. The concept of cutting is one of the earliest and most profound, species-defining ideas discovered by man. The use of sharp-edged tools has been the basis for humanity elevating itself to conquer our surroundings. For better or worse, it has allowed us to exploit our environment and transform raw materials into tools and objects that further enhance our natural capacity. It's intimately woven into our lives and continue to transform human civilization even today. The first recorded evidence of humans using sharp objects dates back to the Lower Paleolithic era, around 2.6 million years ago. These early hominids, known as Homo habilis, used a crude form of stone tools called choppers by archaeologists. They were formed by the chipping away of flakes, characteristically on one side of a pebble with a hammerstone, forming a sharp edge. These primitive handheld stone tools enabled early humans to cut meats, animal skin, and furs, but more importantly, it also empowered early man with the ability to create more advanced tools through woodworking. Cutting is one of the more intuitive forms of material manipulation that we experience. In its most elemental form, it is the separation of a physical object through the application of a highly directed force. For this cutting force to be effective, the tool used to apply the force must be more resistant to localized deformation than the material being cut. In effect, the cutting tool must be harder than the material to be cut in order to effectively transfer the tool's force. As the cutting tool imparts a shear force onto the material, stresses at the contact point of the tool begin to build. As this increases, the material will start to deform. If this force is taken beyond a certain point, the material's elastic limit will be exceeded and the deformation will become permanent. Beyond this threshold, the material has reached its ultimate strength and will undergo structural failure, hardening at the cutting tool. Humanity's next major advancement in cutting tools would occur as we transitioned from the Stone Age to the Bronze Age. During this transition period, starting around 6000 BC, known as the Copper Age, humans started to experiment with smelting copper. Copper's relatively low melting point and malleability made it easy to form into sharp-edged blade tools such as knives and axes. It was also highly abundant, and it often appeared in pure form, ready to simply be picked from the ground. Early metalsmiths started to experiment with the process of alloying. Alloying is the melting together of multiple metals in a precise combination to form a specific material known as an alloy. It would eventually be discovered that adding metals like tin to copper formed a harder alloy known as bronze. Occurring roughly between 3300 to 1200 BC, the Bronze Age marked humans' first prolific use of metal tools. Even though cutting tools and weapons from bronze easily dulled and were susceptible to corrosion, their sharpness and slim design proved to be superior to any stone blade tool. One of the more technologically prominent features of the Bronze Age was the emergence of metallurgy. This study of the physical and chemical behaviors of metals allowed for the modification of the properties of a metal-based material to better fit an application. Cutting tools, for example, need to possess hardness, resistance to shock or toughness, and high wear resistance. The key to understanding how the physical properties of metals can be manipulated lie within its microstructure. At the atomic level, the atoms in metals are arranged in an orderly three-dimensional array called a crystal lattice. However, this crystal lattice never spans the entire material, but rather grow in small structures as the metal undergoes a transformation from a liquid to a solid crystalline phase. These are known as grains, and they each contain their own fairly consistent array pattern, though their structure typically forms with irregularities within that pattern. When an irregularity within a grain creates a disruption in the structure such that it causes a misalignment of an entire plane of atoms in the crystal lattice, a defect known as a dislocation is created. Under force, dislocations provide a mechanism in which planes of atoms can slip and readjust on each other. This shift in structure, traversing the material, is what causes metal to become plastic and permanently deform. Alloying is one method to stop dislocations from spreading. In an alloy, some of the atoms within the structure of the base metal are replaced with atoms of the alloying elements. Known as a solute, the added atoms have different bonding properties than the base metal and can either attract or repel the extra atoms in a grain's irregularity, pinning it in place and stopping dislocations from moving. Dislocations are also impeded by the region between grains called a grain boundary. Because a dislocation can no longer traverse through this boundary to a discontinuous grain structure, controlling the grain size within metal allows us to control its hardness. Smaller grains create more grain boundaries, making it more difficult for dislocations to travel throughout the material and increase its hardness. The size and number of grains within a material are typically manipulated by controlling the rate of crystallization. Heat treatment techniques are typically used in this process. Strain hardening or work hardening is another process for making metal harder. This technique relies on the purposeful plastic deformation of the material. When a metal is plastically deformed, dislocations move and additional dislocations are generated. The more dislocations within a material, the more they will interact and become pinned or tangled. This will result in a decrease in the mobility of the dislocations and the hardening of the material. Because strain hardening relies on creating more dislocations, it must be done at a temperature low enough so that the atoms cannot rearrange themselves, undoing the process. Towards the end of the Bronze Age, advances in furnace design allowed for more oxygen to be fed in, creating higher temperatures. Known as a bloomery, these smelters were now capable of processing iron. The extraction of usable metal from oxidized iron ores is far more difficult than copper and tin smelting. The initial appeal of iron was its economic viability due to this abundance and the singular nature of its use. At very high temperatures, iron begins to absorb carbon. At around 2.5 to 4.5% carbon content, pig iron is formed. Pig iron suffers from brittleness due to its high carbon content, making it less than ideal for working and shaping. Bloomeries generally mitigated this by not fully melting the iron, but rather hot working it above its crystallization temperature. The bloom would be forged mechanically to consolidate and shape it, expelling impurities as slag in the process. As metallurgists became aware that the high carbon content in iron was the root of the problem of brittleness, they experimented with more practical methods for reducing the carbon content to make iron more workable. The next development in furnace technology was the blast furnace. Blast furnaces could fully melt iron ore in bulk, creating pig iron. The pig iron was usually cast into ingots and used as an intermediate material for further processing. Blast furnaces dramatically increased iron production, and they became very common in Europe during the Middle Ages. By the late 18th century, iron makers learned how to transform cast pig iron into a low carbon content wrought iron using puddling furnaces. The furnaces heated molten iron, which had to be stirred by puddlers using long, oar-shaped tools, allowing oxygen to combine with the molten pig iron and slowly remove carbon. Masses of iron would accumulate in the furnace as this occurred. Puddling furnaces could be used to produce cast iron, a low-carbon, brittle but extremely castable and wear-resistant form of iron. These qualities made cast iron the primary structural metal in the industrializing world during the 19th century. When the carbon content of iron is reduced to below 2%, the alloy steel is formed. Overall steel is far stronger and harder than iron, but also far less brittle. Its properties can also be modified by alloying it with elements such as manganese, chromium, vanadium, nickel, and tungsten. Up until the late 19th century, humans had produced very little steel due to the difficulty in removing carbon from iron. Even with the advent of puddling furnaces, the iron industry struggled with inefficient production processes, making steel an expensive and unproven metal for structural use. Working as a two-man crew, a puddler and a helper could only produce about 1,500 kilograms of low-carbon iron in a 12-hour shift. Furthermore, the strenuous labor, heat, and fumes caused puddlers to have a very short life expectancy, with most dying in their 30s. The industry as a whole suffered from a lack of automation. In 1856, engineer Henry Bessemer came up with a more efficient way to introduce oxygen into molten iron in order to reduce the carbon content. Known as the Bessemer process, the technique blew oxygen through the molten metal, converting the carbon to carbon dioxide. The process was inexpensive and effective, though overly aggressive. It would later be refined by the addition of Spiegelisen, a ferromanganese alloy that helped reduce impurities while maintaining the correct carbon levels in the Bessemer process. Other later refinements included the addition of limestone to help remove phosphorus from the process, further reducing the brittleness of the steel produced. This innovation caused steel production costs to dramatically decrease. The price of steel rails dropped more than 80% between 1867 and 1884 as a result of this new technique. The growth of the world's steel industry had begun. By the 1900s, the Bessemer process would be replaced by the more efficient open hearth process developed by German engineer Carl Wilhelm Siemens. This new technique allowed quantities as large as 100 tons to be made in a single furnace. The explosion of the steel industry directly led to the world's first corporation valued at over $1 billion in 1901, Andrew Carnegie's U.S. Steel Corporation. As the industrializing world pivoted towards the use of metal as the primary engineering material, a new class of techniques for shaping and forming metal would evolve, and they all relied entirely on the process of cutting. Unlike using sharp edges on much softer organic materials, cutting metal efficiently requires high levels of rigidity, precise control, and large amounts of force. To deal with this problem, apparatuses known as machine tools were developed that could apply force to a cutting edge in a highly constrained manner while rigidly holding a workpiece. The first primitive forms of machine tools were based on rotation. Powered entirely by hand, the bow lathe allowed soft materials like wood and some soft metals to be shaped as it rotated or turned. The concept would eventually grow into larger lathes powered by treadle power, animals, flowing water, and eventually steam power. When inventor James Watt first experimented with his steam engine, the need for perfectly bored cylinders led to the development of the first true machine tool, a variant of the lathe called a boring mill. Invented by industrialist John Wilkinson in 1774, the water-powered machine could bore a cylinder 1 meter in diameter to within an accuracy of less than 1.5 millimeters. By 1800, the first lathe capable of cutting accurate screw threads was designed and constructed by Henry Maudslay, an English toolmaker. Maudslay's screw-cutting lathe combined a lead screw with a movable rest, allowing for the first time accurate repositioning of the cutting tool in between cuts. This mechanism of cutting tool control became the progenitor for virtually all modern machine tools. The next major development in machine tools came as an evolution of the lathe. In a lathe, the workpiece is rotated as the stationary cutting tool moves along it. In a mill, the cutting tool itself is powered as it traverses the workpiece. In 1820, American inventor and manufacturer Eli Whitney pioneered the use of milling in order to mass-produce muskets. The concept of machine tool-based mass production in which parts were produced interchangeably was revolutionary for the time. It even prompted the United States to adopt a standard measurement system in order to standardize part production between armories. By 1875, the standard set of machine tools used by modern manufacturing had been established. Lathes, mills, grinders, shapers, saws, and broaching machines were all in use by contemporaries of the new age of mass manufacturing, with many of these precision machines easily achieving accuracies down to 25 microns or a thousandth of an inch. A central electric motor power source would take over steam, with integrated electric motors soon becoming the norm by the turn of the century. In the late 1940s, driven by the United States Air Force's search to increase complex aerospace part production, a new method for controlling machine tools in an automated manner using coded instructions on punch tape was devised. The concept, which was spearheaded by MIT's Servo Mechanism Laboratory, relied on an electronic processor to control the motion of the machine tool from a program, as well as a computer to program the instructions for the machining operation. In 1955, the term NC or numerical control was coined as this new form of machine tool became available to the industry. By the mid-1970s, due to the explosion in integrated circuit manufacturing, these machines began to adopt fully computer-based operational workflows. Known as CNC or computer numerical control, these new class of machine tools initiated a level of automation never before seen in industry, not only allowing machines to achieve accuracies well below 25 microns, but also unprecedented levels of repeatability, producing thousands of parts from a single program with no significant deviation between them. This massive paradigm shift single-handedly took the millions of years old practice of forming an object by manipulating a cutting tool with our hands to the notion of forming materials through abstract computer instructions. Unlike simple hand-powered bladed tools that produce a slow, relatively low-force cutting action, the rise of machine tools created a new level of demand on cutting tools. They would quickly grow to large, rigid behemoths that could focus greater amounts of power and thus force through a cutter. Faster feed rates and more aggressive amounts of material removal were now possible, pushing the limits of cutting tool materials of the time. Similar to their hand-powered counterparts, the tooling used in machine tools required both hardness and toughness. But because of the relatively aggressive nature of their use, Hardness at an elevated temperature, or hot hardness, and wear resistance both become important characteristics. The carbon steel that prevailed during the Industrial Revolution, while hard and highly resistant to abrasive wear, began to soften at temperatures as low as 150 degrees Celsius. This limited them to light machine use and hand tools. In 1910, the first of a new class of alloys were introduced by the Crucible Steel Company to specifically address the limitations of carbon steel in metal cutting. Known as high-speed steels, these alloys could withstand increased cutting speeds and higher temperatures without softening. They achieved these properties from a variety of alloying metals added to a steel containing between 0.5% to 1% carbon. These alloying metals are typically tungsten, molybdenum, or a combination of the two at around 10% composition. They were also alloyed with other elements such as chromium, vanadium, and cobalt to modify their properties further for application-specific needs. Many surface treatments have also been developed in an attempt to extend the life of high-speed steel tooling. One of the oldest and most common coatings is black oxide. Commonly appearing on drills and taps, a black oxide surface treatment is done to deter the buildup of work material on the tool. One of the more contemporary coatings used on high-speed steel is titanium nitride. This coating is applied by the process of physical vapor deposition at a temperature low enough to prevent significant changes to the tool's heat treatment. Titanium nitride can extend the cutting life of a cutting tool significantly, by as much as 3 times, and permit operating speeds to be increased by up to 50% when compared to raw tooling. Titanium aluminum nitride would also eventually supersede titanium nitride in higher quality tooling due to its better performance at higher temperatures. Special high-performance alloys known as cast alloy tooling that eliminate iron entirely have also been developed. These enhanced durability tools further improve the hot hardness of regular high-speed tool steel at the cost of increased brittleness. They're generally used for cutting metals with hard inclusions as well as tough, scaly material. It also should be noted that most of the alloying elements found in modern tooling are not abundant in supply and are generally sourced from a handful of countries. Cobalt, for example, is primarily sourced from the Democratic Republic of the Congo, while China is the largest supplier of molybdenum. The relative scarcity and reliance on a small group of suppliers directly affect the cost of tooling, resulting in a global upwards trend since their introduction. The next major advancement in cutting tool design got its start in 1893 by Henry Moissan during a search for a method of making artificial diamonds. While charging sugar in tungsten oxide, he melted tungsten subcarbide in an arc furnace. The carbonized sugar reduced the oxide and carburized the tungsten. The material produced was tungsten carbide, and it was extremely hard, approaching the hardness of diamond and exceeding that of sapphire. It was also almost 16 times the density of water. Despite these properties, it was extremely brittle and had very little industrial use. Almost 40 years later, combining tungsten carbide with a cobalt binder would result in the release of the first commercial carbide tooling that exhibited superior performance in the machining of cast iron and non-metallic materials, though cutting steel would prove to be far too erosive. Further development would result in the replacement of part or all of the tungsten carbide with other carbides, especially titanium carbide or tantalum carbide. This led to the development of modern multi-carbide cutting tool materials, permitting the high-speed machining of steel. The process of manufacturing carbide-based tooling, or cemented carbides, differs dramatically from previous cutters made of molten metallurgy. The process begins with the careful ball milling of the constituent compounds into a powder that includes a binding agent. The powder is then compacted into a shape at a pressure exceeding 2,000 atmospheres and finally sintered at around 1,500 degrees Celsius. Because cemented carbide tooling can be formed easily into any shape, this brought about the use of insert tooling in which replaceable cutting inserts are mounted to a metal tool body. This made it possible to effectively service only the cutting edges of a tool, eliminating the need for costly tool sharpening, especially in large-scale manufacturing. Much like high-speed steel tooling, by the 1970s, carbide tooling would also see the application of high-performance coatings through physical vapor deposition that enhanced their performance. Coatings such as titanium nitride, titanium carbide, ceramics, and even diamond would further reduce tool friction and offer greater resistance to abrasive wear and cratering, especially in tougher, more abrasive materials. Cemented carbides are much harder than steel tools at room temperature, but their true advantage lies in the fact that they do not rely on heat treatment for their hardness and can retain it even at elevated temperatures. This allows carbide tooling to be run faster and more aggressively than metal tooling, though the nature of their manufacturing process makes them very brittle and susceptible to shock. Other more exotic forms of tooling are ceramic cutting tools, natural diamond, and synthetic polycrystalline diamonds. These all share a common characteristic of being extremely hard, especially at very high temperatures, but also being brittle to the point of having limited use. These exotic cutters are generally used in applications where light, smooth, high-speed cutting is done on very hard work materials. It should also be noted that the very same high hot hardness properties of these materials make them ideal for abrasive machining. In abrasive machining, a hard abrasive aggregate such as carbides, ceramics, or diamond are cemented into a tool such as a grinding wheel. When brought into contact with the work material, each particle of abrasive makes a cut, resulting in a net bulk removal of material. As a particle dulls from wear, the friction of its dull edge dragging on the material forces it to break away from the tooling, wearing down the grinding tool and exposing a fresh particle. Because grinding can remove small amounts of material in a highly controlled manner, it's ideal for shaping very hard materials with great precision. One drawback to the process is that the friction caused by dulling aggregate generates significant amounts of heat within the workpiece, though this can be mitigated with cooling for precision work. While non-mechanical methods of cutting materials have been developed, such as laser cutting and erosive electromachining processes, such as electrical discharge machining, none have been able to replace the versatility and efficiency of mechanical cutting. Manufacturing has now entered a new era of diverging principles in which the emergence of additive processes such as 3D printing look to dethrone the practice of subtractive material forming. While still the dominant technique for now, the centuries-old methods of milling, turning, broaching, and grinding is still being met with more widespread use of automation and integration, lowering costs and improving accessibility, shoring up its future as the go-to method of parts manufacturing for decades to come.
Towards the end of the 20th century, the advent of CNC technology brought about an evolution in how machinists operate, transferring their manual actions to code-based operations. Thinking in code has permeated a vast array of once manual industries and has become a critical problem-solving skill. And a great way to learn how to approach problems programmatically is Brilliant.org. Brilliant is where you discover the thrill of learning with thousands of captivating interactive lessons in math, data analysis, programming, and AI, designed to unleash your potential and transform you into a confident problem solver. Brilliant is a groundbreaking educational platform that distinguishes itself by employing a first principles methodology, empowering a robust understanding of fundamental concepts. Every lesson is filled with interactive problem-solving exercises with encouraging active participation and engagement, a method proven to be 6 times more effective than passively watching lecture videos. Furthermore, Brilliant's content is crafted by an esteemed team of award-winning educators, researchers, and industry professionals from renowned institutions such as MIT, Caltech, Duke, and prominent companies like Microsoft and Google. Brilliant immerses you in active problem solving because truly grasping a concept demands more than mere observation and memorization. You need to experience it. By engaging in hands-on learning, you not only build real-world knowledge on specific topics, but also develop critical thinking skills that make you a better thinker overall. Investing in daily learning is paramount for personal and professional development, and Brilliant makes this convenient and enjoyable. With captivating, digestible lessons that seamlessly integrate into your daily routine, you can build genuine knowledge in just a few minutes each day. Say goodbye to aimless scrolling and embrace a more rewarding way to spend your free time. A great introduction to coding I highly recommend is Brilliant's Thinking in Code course. In this series of lessons, you'll build a solid understanding to attack problems in a logical, algorithmic manner, allowing you to build solid foundations for computational problem solving. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/newmind or click on the link in the description below. You'll also get 20% off an annual premium subscription.